Okay, here we are in module. Let's see, module 11B. We'll look at the properties of air and water systems again. Do some mass balance, some simple mass balances, and look at what we call the psychrometric chart, which is a really convenient way of representing the properties of air-water mixtures. Okay, the air-water systems. First thing we want to do is define what the dew point temperature is. And the dew point temperature, if you have air with water in it, the dew point temperature is the temperature at which water begins to condense when a mixture is cool. So if you wake up in the morning, you'll notice that often there's dew on the ground, and it turns out that that's when the air is saturated with water. When it gets saturated with water, dew will start to form, or you'll see fog. Those are indications that you have a saturated air, and it usually occurs when the temperature cools. Typically, air has a certain amount of water in it, and warm air can hold more water. So as you start to cool the air down, like overnight, then the air can no longer hold that amount of water, and so dew will start to form and precipitate out of it. The dew point, the temperature, if you cool the given air mixture, at what temperature will it start to condense water out of it? Let's take an example. Suppose I want you to find the dew point of atmospheric 33 degree air, and we're in metric units, having a relative humidity of 80%. Well, relative is relative to saturation, and you recall that saturation was the partial pressure of the water in the air divided by the partial pressure of the water in the air if it were saturated. So that is, here we have YWP, there's the partial pressure. And recall at saturation the partial pressure equals the vapor pressure. So we take the saturation or vapor pressure of water at 33 degrees in the denominator. And in the numerator we have the actual partial pressure, call that P sub A, of the water in the air. And the ratio of those is 80% in this case, and then we call that the relative humidity. So from this we can calculate the mole fraction of water in the air. The mole fraction turns out to be, plug in the numbers, and we wind up with the mole fraction of 0.0399 moles of water per mole mixture. Now if we consider what temperature will give us that mole fraction at saturation. So we had 33 degree air, which is fairly warm, humid air, and now what would we have to cool it to for it to be saturated? So YWP would equal P saturated at the dew point. So the temperature that gives us this Y that we already know is 0.0399 times the pressure, which we're looking at 1 atmosphere, which is 1.01 bar, or the vapor pressure at the dew point would be 0.04 bar, 0.0403. In your steam tables, you'll find that that occurs at a temperature of 29, a little over 29 degrees C. So cooling it down from 33 to 29, we've reached the dew point. So that's what the dew point is. All right, let's take a look at a typical air conditioning process. And here we have an evaporator. Typically this is an evaporator in an air conditioning system. And we'll run R134 through the evaporator. So this is coming in cold, very cold. And air will be blown across it, across the evaporator. This is a heat exchanger. And as the air is blown across the evaporator, typically what will happen, particularly in the humid south, you will see the water droplets start to form onto the coils or onto the heat exchanger surface, and that water will drop out as liquid because the air has become saturated as we cool it. Again, when you cool to a temperature at or below the dew point, water will start to form, or liquid water will start to form, and then we have to take that out as condensed water. So air conditioners, if you notice when you park your car in the summer and go in, come back out, drive away from a parking spot with your car, you'll notice there's a liquid pool underneath it. That's from dew, or let's say condensate, that's formed in your evaporator and dripped out underneath the car. Not to be concerned. Okay, typical AC process, the flow of the dry air portion. Now, to do the calculations, we define a dry air portion of the mixture, the air-water mixture. As you go through the evaporator that we just saw, let me go back to that. As you go to that evaporator, this dry air, all the air will go through here and come out here. The mass of the mixture will not be the same in and out because we've taken out some water. But for convenience sake, we like to keep the dry air part constant. So for this reason, the air properties are tracked as mixture property per kilogram of dry air. So this, instead of many of our properties of mixtures, we've talked about mole fractions. Now we're going to talk about mass ratios or volume ratios. We do things per kilogram of dry air because we know the kilograms of dry air coming into the process, into this evaporator, is the same as the kilograms of the dry part of the air coming out of the process. Even though the total mass of this state 1 and the total mass of state 2 are not equal, the amount of air in state 1, dry air part, and dry air part in state 2 are equal. Now, if we recall omega, we calculated this property earlier as the kilograms of water in the mixture per kilogram of dry air. That's a mass ratio. Also, we have a property called the volume of the mixture, which is often given in meters cubed of the total mixture, that's water plus air, per kilogram of just air. And again, this is a sort of a ratio rather than a fraction. We'll also take the enthalpy to be kilojoules of the mixture per kilogram of just air. And this is for convenience sake when we start doing process calculations. Let's do the volume calculation and show you how that's arrived at. At low pressures, then air will behave as an ideal gas. So we'll take PV of the mixture is equal to mass over molecular weight of the mixture, RT. If we take the partial pressure of the air times the volume mixture, that's just the mass of just the air over the molecular weight of air times RT. And we add the partial pressure of the water, P minus P water. I'm sorry, this is yes. Again, P air times the volume of the mixture. But P air, since the partial pressures add up to the total pressure, the partial pressure of the air is the partial pressure as the total pressure minus the partial pressure of the water. What's left over is the air, is equal to m of the air over the molecular weight, RT. Then we can add in the, find the volume of the mixture per mass of just air, solving, let's see, this equation is equal to RT over the molecular weight of air times P minus P of the water. And that gives us an ability to calculate this volume of the mixture in these, I would say unorthodox units, where it's the volume of the mixture per mass of just the air in the mixture. Per kilogram of air, let's say, or per pound of air if you're using metric units. Now to calculate the enthalpy, we'll take H of the mixture, that's the air-water mixture, is equal to the enthalpy of the air in the mixture plus the enthalpy of the water in the mixture. Now the H of the mixture then per mass, or let's say per kilogram of air, per kilogram or pound mass of air is the air's enthalpy plus the omega, which is the mass of water per mass of air, times the enthalpy of the water at the given condition. So let's look at the units of that. H kilojoules of just the air per kilogram of the air. H of the water, kilojoules water per kilogram of water, times this mass ratio, kilograms of water per kilogram of air. So let's see, the kilograms of water cancels, and we wind up with kilojoules of water per kilogram of air plus kilojoules of air per kilogram of air. Gives us all the overall H of the mixture, as you see here. Now we can calculate H of the air relative to some reference state, and that, when you have a psychrometric chart, the reference state should be stated on the psychrometric chart what temperature the air is referred to, and so the H's listed will be relative to that temperature. And so H of the air is Cp times T minus T reference. Often the psychrometric charts that you'll find have a reference temperature of 0 degrees C, and so if it's in metric units, then just 1.005 times the temperature minus 0 would give you the enthalpy. Now that's just the air part of it. That's just the dry air. We also have the enthalpy of the water vapor that's in the mixture. And most psychrometric charts will refer the water to the same reference point as the steam tables. So you can look up Hg from your steam tables, add the temperature of the mixture, that's H of the gas, add the temperature of the mixture. And if it's an ideal gas, then Hg is a function of temperature only. So you could look up almost any pressure and find the proper Hg, as long as it's a low enough pressure. So Hg at T reference plus Cp times T minus T reference would be equal to H of the that's Cp of the water vapor, would give you H of the water vapor. This turns out to be, for a reference point of 0, the Hg is 2501, and you can have actually a formula to calculate H of the water vapor. Putting it all together, you can get the H of the mixture. Now, if you want to find H of a liquid, because when we're doing energy balances, remember we have this evaporator, and this is going to be a common sort of thing, where the air blows and gets cooled by the evaporator, liquid comes out, and so you want to know the enthalpy of that liquid. So that will be simply Cp of the liquid times T minus T ref. T ref is 0 degrees C. So that's just Cp of a liquid, which is approximately 4.9 for liquid water, times T. The reference state for that we often use, and we're going to talk about psychrometric charts in a minute, are H equals 0 at T equals 0 degrees C. And for water, H liquid is 0 at T equals 0 degrees C. And again, when you're finding steam properties, sometimes it's just as easy to look them up out of the steam tables. Okay, here's a process that's very interesting, called adiabatic saturation. And this is very useful, particularly in dry climates, to cool the air. We bring air in, and then we saturate it. We add water to it, and we wind up with cooler air, because it takes energy to vaporize this water. Energy comes out. Say that's hot air. This would be cooler air, because the energy to vaporize the water is taken out of the air and the temperature drops. When we say adiabatic saturation, we assume we're saturating at approximately the outlet temperature for the liquid water coming in. The energy balance becomes This is like doing a mixing chamber that we talked about earlier. Mass of the air times H1 plus mass of the liquid, H of the liquid, equals mass of the air times H2, because remember these H's are kilojoules per kilogram, just air. Apply that water balance. Now we're doing a mass balance on the water. We can find the mass of the liquid that has to be used to saturate the air. It's equal to m air omega 1 plus m liquid equals m air omega 2. That's a mass balance. And we can get the two balances to describe the process. Now this process is closely modeled by what we call the wet bulb temperature. What we do is we put a sort of a wicking material onto here that soaks up water. I say a shoestring. You could use a shoestring and moisten it. Blow air across here, and as the water evaporates, it cools the air, and this temperature will drop below what we call the dry bulb temperature, where there is no shoestring. Dry bulb temperature is just the regular temperature, and the temperature will drop down as the water evaporates and reach an equilibrium. That is called the wet bulb temperature, and it's pretty close to the same thing as saturating the air. So the adiabatic, what we call the adiabatic saturation temperature, and the wet bulb temperature are very closely related to each other, practically the same thing. So far we looked at properties of air-water mixtures. We looked at the dew point, the wet bulb temperature, the dry bulb temperature, relative humidity, mole fraction. These properties we know how to find. Specific humidity, remember that was what I call absolute humidity, omega, the enthalpy, and the volume, and the partial pressure. So let's take an example. For an air-water mixture at 85 degrees C and 60% relative humidity, find all the other properties. For this we can either do it by all the calculations we just did, or we can use this psychrometric chart. And that's a very handy tool to use, psychrometric chart. Here you see you have different lines for different relative humidities. This is called the saturation line, where air is saturated with water, or saturation curve. And the relative humidity here is 100%. As you go down to lower and lower, and by the way, this is what we call omega, the absolute humidity, or the specific humidity, the pounds of water per pound of air. And it's a measure of the absolute amount of water in the air. The relative humidity is compared to how much the water can hold, how much water the air can hold. And so if I take my example, where I had, let's go back, change that example to 40% relative humidity, what I truly have here. Then you'll find that at 85 degrees and 40% relative humidity, we draw it. If you get out a psychrometric chart from your text, draw this on here and find where those two intersect. Here's the temperature down here versus 85% relative humidity. We'll find if you bop over here a little bit, we can find the absolute humidity. This is a little over 0.01 pounds of water per pound of air. Now you recall the dew point is the temperature at which we cool. Now if you cool the air-water mixture, you're going to lower temperatures. Cooling is in this direction. If we cool that air, then the absolute humidity doesn't change. There's still that water in the air until you get it saturated. Once you get it saturated, now you'll be able to form droplets that will take the water out of the air and cool it along the saturation line. But if we just stop at the dew point right here, then we'll find the dew point. We can read the temperature here and find the dew point is approximately 57.5 degrees Fahrenheit. So there's your dew point. Let's look at another property one might find. Here we found omega is 0.0102 approximately, and T dew point is 57.5 for this air-water mixture. Usually what you do is you'll take the psychrometric chart and you'll mark two properties and mark your point and then find the others. Very convenient, this chart. Let's look at another property, and I don't have this one, the lines shown on this particular chart, but if you take out a chart from your text, you'll see these lines that go like so. And this represents the equation we put up earlier for enthalpy. Enthalpy lines run at approximately this angle. And actually, you'll see the wet bulb temperature lines run fairly parallel to those, because adiabatic saturation is very much as keeping the same enthalpy of the mixture. And so if you read this off, and I suggest you stop now, take the point that we defined, and find the enthalpy, you'll find it's pretty close to 31.8 BTUs per pound of air. Go ahead and use your English units table. And that the wet bulb temperature is approximately 67 degrees. So this tells you something, and this is used in dry climates quite a lot. If our humidity was 40%, and often in a dry climate you can have drier air, you can have even very dry air down 20%. If you take that air at 85 degrees and it's 40% relative humidity, and you follow the dew point line, which is approximately parallel to the enthalpy line, as you cool it, you'll get the wet bulb temperature, or in our case, right about here, 67, 68, something like that, pretty close to 67 degrees Fahrenheit. So by just spraying water into the air, which is what the wet bulb temperature really tells you, or the adiabatic saturation temperature, spraying water into the air can cool the air significantly to where you go from 85 degree air with relative humidity of 40% to 67 degree air with relative humidity of 100%. Now that'll be cooler air. It may not be super comfortable because now it's saturated with water. Finally, off the psychrometric chart you can find the volume, which is something you could calculate again like we did earlier with the ideal gas equation, or you could just read it right off the chart. You'll see here the volume lines run approximately in this direction, and this will be, I think this was, if you find between two lines, you'll find that this volume here, if you carefully read it, is approximately 13.96 feet cube per pound of dry air. So we looked at air-water properties. They depend on the amount of water in the air, and they're often expressed per kilogram of air. So unusual units, but very convenient. And we've done balances. Air balance, which is if you use these units of per kilogram of air, then typically in an air conditioning process the air in will be equal to the air out straight through 0.1 to 0.2. We've done the water balance, and we looked at the evaporator where water was condensing out. Some water came in with the air at state 1, let's say, and some water came out with the air at state 2, and then you have some liquid water. So you have to balance the water in and out of the process. We've done an energy balance. That's pretty much it for properties. We looked at the psychrometric chart, found the properties of air-water mixtures from the chart. And one thing I haven't pointed out, but the charts are usually built, you can build your own chart of course, but charts that you'll find in your text, for instance, are usually built for atmospheric pressure. You change the pressure, you change the chart. For atmospheric pressure, because these charts are primarily used for air conditioning or environmental type problems where the air pressure is the same as the atmosphere. Obviously, if you lived up in the mountains, you'd have to build a slightly different chart. So for homework, I want you to use the equations we developed to check the above results that we got from the psychrometric chart. Now you have to be careful, find the reference state in English units to do that. And from Chapter 14 solve these problems, which are pretty well directed to finding properties in the psychrometric chart and otherwise. So that's it for 11B.